Okay, so we know that there's a centripetal force because this thing is going in a circle. So we write this down because it's always true. But what we have to do is identify what the centripetal force is. Well, we did that with our force diagram, Fs max. So all we have to do is write this thing is equal to Fs max. And that, of course, is equals mu Sn, which, of course, is mu S mg. Great! Now, what do we want? How far can the block be placed from the center of the turntable before it slips? Okay, well, we got to get an R, right? That's the R. So we're going to say that this equals this. All right, so we have mv squared over r equals mu S mg. Okay, what do you notice? The masses cancel. Okay, now we want to solve for r, so we multiply both sides by r. Then we divide by mu Sg. So there you go. So the answer is, so r equals v squared over mu Sg. So that's how you do it. Now, notice, it doesn't depend on something. This does not depend on mass. So next time you're on something like this, try it. Try it with people that have different masses. See if it's true. It is. What does it depend on? The velocity. That makes sense, right? If this thing is going at a really slow speed, you know, you can stand way out here, right, and not fall off. So that makes sense, but also it depends on friction. That makes sense too, right? I mean, if it's ice, good luck, you know. If it's sandpaper or something like that, in other words, if this is large, then it will work. Okay. What? All right. Let's do another example. Let's do another example. Okay, we're going to talk about, so you're driving a car and we're going to make a turn. And that we're going to assume that the ground is level, so we call it an unbanked turn, okay? So basically, you know, and we're going to have a circular turn, because, you know, what else, right? We're talking about circular motion. So, you know, you just imagine you're going, and then you make a circular turn. I don't care left or right. All right, now, Newton's laws tell us we're going to go straight unless there's an external force acting on us. All right? So, we want to make a turn. What are we going to do? Turn the steering wheel. Well, what's the external force, though? Right? What's the external force that's allowing us to make a circular turn? So, have you ever driven on ice? If you turn the steering wheel and you're on ice, is it going to help? No, it's not. So, what's the external force? Friction, right? Friction between the tires and the road. Okay, now what kind of friction? Is it static or kinetic? Now think carefully about this. Do you want to maintain contact with the road, or do you want to skid? You want to maintain contact, right? So it's static friction. Okay, here you go. Now we're making a circular turn. Therefore, there has to be a centripetal acceleration, right? Therefore, there has to be a centripetal force. So that centripetal force is static friction. So isn't that nice and easy? Whenever you make a circle, it has to be a centripetal force. As simple as that. Okay, so here's the picture. So rear view of the car, centripetal force towards the center of the circle. Top view of the tire, so it's making this turn, right? Center of the circle. So this static frictional force prevents the tire from slipping, right? We don't want to slip, right? For instance, tire from slipping sideways. So let's do it. So I'm going to do this one, and you'll do the next one. Okay, okay, so obviously, I just said that, forget it. All right, you are driving your car at a constant velocity and are approaching an unbanked curve level, right? How fast can you drive your car and still make the turn before your tires begin to slip? Well, you know, this is a circular motion problem, right? And so as soon as you see that circular, and look at, they even drew the force diagram for us. Isn't that nice? So there's the normal force, there's the weight, and Fs. And we want to go as fast as we can, so it's Fs max. So there's your force diagram. This is the centripetal force. So what do? You do what you always do. We just write down the sum of the centripetal forces equals mv squared over r. All right, that's always true. But you have to identify the centripetal forces. Well, the centripetal force is only one. It's Fs max. Okay, we're going to skip some steps now, which is mu s n. And what's n? It's the weight, no kidding. So it's mu s mg. So we want to get the velocity. So we're going to put this equal to that. So we have mv squared over r equals mu s mg. And look what cancels again, mass. So we want velocity, so multiply both sides by r. We get v squared equals mu s g r. And we want v, take the square root, both sides. There you go. Now, again, independent of mass. Doesn't that make sense? I mean, can you imagine if the people who designed highways had to worry about the mass of the car or the truck? I mean, it'd be crazy, right? I mean, what would you do? You have this big semi-truck, and then you have this little tiny Cooper car? I mean, you know. Okay, so it doesn't depend on mass. What does it depend on? Well, it depends on the friction. That sort of makes sense, right? If it's ice, you're not going to be able to make a very good turn. It depends on the radius of the turn. If it's a really gigantically large radius circle, well, you can go really, really fast. If it's a really tight circle with a small r, you got to slow down. So this makes really good sense. Okay, so for unbanked, we have velocity equals square root of mu s g r. Okay, and we're going to do bank next. All right. This is what we mean by a banked curve. So it's not level. So let's say we're driving a car at a constant velocity, and we're approaching a banked curve. All right? Now, to make it exciting, we can't turn the steering wheel. Whoa! Now, once again, you know, Newton's laws say that you're going to keep going in a straight line, constant speed, unless there's external forces acting on you. Okay? So, now, my gosh, what are the forces acting on you? I mean, you know, what are the forces? And again, all we want to do is think about, well, here you go, right? Oh, by the way, sorry, I forgot to tell you something. We're ignoring friction. So you can't turn the steering wheel, and there's ice. So what are the forces acting on you? There's a normal force, and there's the gravitational force. That's it, right? So, okay, so this is the bank, right? Some angle theta. And so, you know, this is the road. This is perpendicular to the road, so there's the normal force, and there's the weight. And this is the center of the circle. So we've been talking about how there has to be a force that points towards the center of the circle. Oh, yeah. Look at this. This is the top view, right? And this is the side view, the rear view. So there's that angle theta, okay? All right, there has to be a centripetal force. There has to be. So What is it? I mean, I want a force pointing in that direction. Well, this is not going to help me, is it? But, oh, what can I do with this guy? What do you do with a vector that points in some direction you don't like? You resolve it, right? You resolve it. Ding, there you go. So we resolve it into this piece, into this piece. Of course, that piece is the same as that piece, so who cares, right? So we resolve it into that, into that. This is the force that points towards the center of the circle. So this is the centripetal force. So what is that? That's n sine theta. So n sine theta is the centripetal force. All right. So you're driving a car at a constant velocity. You're approaching a bank curve. How fast can you drive your car and still make the turn before your tires begin to slip? Use Newton's second law. So I would like you, please, you do this. Do it yourself. So pause your video, basically follow what I did here, but it's a little bit different. But please figure it out yourself. All right. So I'm assuming you did it. Okay. Now let's do the z forces first. Just you'll see why. So the sum of the z forces, that's okay. This is n cosine theta, right? N cosine theta. And cosine theta minus mg, that equals 0, right? The car's not going like this. Okay, so therefore n cos theta equals mg. Okay, we didn't have to do that first, I just felt like it. Now let's do this one. Okay, we know it's going in a circle, so we know there's centripetal force. So we just write this down because it's true. But then we have to identify what the centripetal force is, and we already said that. The centripetal force is this, which is this, which is n. This is opposite, so it's n sine theta. So it's n sine theta. Oh boy. Now, we want to solve for velocity. So we know we're going to use this, right? So let's just do it. So let's see. So solve for velocity. Yeah, whatever. Okay, so multiply both sides by r. Divide both sides by m. Let's leave it at that. And now we got to substitute for n, right? We got to substitute for n. So n equals mg over cos theta. So we plug that in. So we have mg sine theta r, and then we have m on the bottom, but we also have a cosine theta on the bottom. So what do you notice? The m's cancel. Well, of course they cancel. Again, can you imagine a highway engineers having to make different roads for a big truck and a little car? No. So the m's cancel. Okay, now high school trig. What's sine over cosine? Tangent. So we have gr tangent theta. And then we have to take the square root of it, right, because that's v squared. So v is the square root of that. So that's v max, right, the maximum speed. So for banked, we have v max equals square root of, so it's g r times the tangent of theta. So you look at this equation for the unbanked, you look at this equation for the banked, what takes place of the friction? The angle, right? The tangent of the angle, okay? So I mean, think about it. Isn't this wonderful? You don't need to turn your steering wheel. You don't need to rely on friction. I mean, you know, it costs a lot of money to build a bank curve, right? I mean, you got to fill that up with dirt and cement and all that kind of stuff. Why would you want to spend all that money? Well, if you live like in Colorado or somewhere where there's a lot of snow, or like Maine, you know, it's a super safety factor because you can just make that turn without any worries about friction. It's wonderful. Okay. What happens for this one, the bank turn, what happens if you go too fast? So if your speed is greater than the square root of GR tan theta, well, that means you're going to slide up the bank. Not a good thing. What happens if you're going too slowly? Then you're going to slide down the bank, right? So, yeah. So you want to go at the right speed. But of course, in the real world, you know, there is a little bit of friction, hopefully. I mean, even in the wintertime, there's usually going to be a little bit of friction. So super, super safe. Okay. Yeah, whatever. All right. Here's a really great question. Now, what's a barrel of fun? So a barrel of fun, so you're standing in this cylinder thing, right? And when you get into it initially, there's a floor, right? And then they raise you up and they start spinning faster and faster and faster. Then eventually, the floor vanishes. So, you know, so you're standing like this person here, going around and around, and you're not standing on anything. You're just looking down at the ground. All right? So anyway, this is a very important question. So pause your video and figure it out. All right, let's answer it. Well, obviously there's weight, right? I mean, there's always weight. And, you know, the person here, she's like this. And so there's, right? So weight is pulling her down, but she's not falling down. She's not accelerating. So it has to be, so what is the force up? It's not a normal force. She's not standing on anything, right? It's friction. So there's a normal force up. Now let's look down on her. Let's pretend we're a bird up here. And we're looking down on her. So there's a cylinder, and here's the person. She's going in a circle. So what does there have to be? There has to be a centripetal force, right? What is it? Well, it's a normal force, right? I mean, if this thing was made out of tissue paper, she'd be out there flying, you know? It's a normal force. So, what's the answer? Well, this is insane. It doesn't point towards the center of the circle. It points away from the center of the circle. This is insane because how do you get a crazy angle like this? Here, there's no friction. She's dead, right? Okay, here, again, this is insane. There's no friction. She's dead. This is the one, right? There's friction, weight, normal. So there you go. All right. That is a good place to stop. Actually, we should have stopped 10 minutes ago, right?